All right. So now we are ready to study the behavior of an LTI system in terms of the magnitude response and more in terms of the intuition. Now that we have the mathematical framework, we are now ready to go for the intuition. Okay. So first thing that we are going to be looking at is the magnitude response. Magnitude response of a first order 0. First order 0. Okay, that means we are looking at a transfer function which looks like this: 1 minus C naught Z inverse. Okay, so this can be written as Z minus C naught divided by Z. And basically this tells us that there is a 0 located, and let us say that this is C naught and this is the pole. So this is the pole at origin, and that is the 0 that we are that we are interested in. Okay, so now what we are going to do is we are going to traverse, to get the magnitude response, we are going to traverse along the unit circle in a counterclockwise direction, and at every stage we want to get the magnitude response. So here is how we are going to be looking at the study of the magnitude response. So so what we will do is to say that we will look at this particular first order system as a ratio of two vector quantities. The two vector quantities are, supposing this is the point of interest where I am interested in, the denominator is given by the vector v1, that is from the pole to the point on the unit circle, and the distance from the from z minus c naught, if this is z e power j omega, that those are the points on the unit circle. So basically are going to be, so what is the distance from the 0? That is given by the vector quantity v3. Okay, so in other words, the ratio that we are interested in is given by this. So if you now tell me compute the magnitude response, then what I will do is I will say at every point on the unit circle I will compute what is v3 and I will compute what is v1. Okay, compute at all points on the unit circle. Okay, I hope you are comfortable with it. So notice that as you start from the origin and come towards this location, okay, let's come, that is the point where you are closest to the 0. That is the point at which v3 will be minimum. Okay, where will v3 be maximum? Look at diagonally diametrically opposite location. When you are from this point, that is the point at which you are maximum away from the 0. What is the denominator contributing for you? Always equal to 1. So therefore the denominator is really not giving you any contribution to your magnitude response. All of the magnitude, all the behavior is coming from the ratio of the v3 by v1. v3 is the one that is varying. So now we can start to sketch what will be the variation that we will see as we go from 0 all the way to 2 pi. Okay, so let us say we start at a particular value at omega equal to 0. So that is the value of v3. v1 is always equal to 1. Then as you increase the angle and you are approaching theta, okay, let us say this is theta, what happens? The magnitude goes on decreasing, and at this point it becomes minimum. After that you will see that the magnitude will increase, and let us say this is pi, and this is so basically what we are looking at is the angle. This is 2 pi, you're diametrically beyond pi. So pi plus theta or theta plus pi, that is where you will expect to see the maximum, and then at 2 pi you will come back to the point at which you started. Okay. So this is 2 pi. So you come back to the, so you will basically it will reach some maximum value and then it will come back here. So I hope you are starting to see how we are visualizing the magnitude response of a first order 0. Okay. Now, supposing I push this 0 a little closer to the unit circle, what will happen? This minimum point will come closer, will come a little lower, and the maximum point will go a little higher, will go a little bit higher, and then comes back to the starting point. Okay. Now, what happens if it touches the unit circle? The 0 goes to the unit circle. Then green dot, it will actually touch 0 here, and then it will go to a peak value and then come down. Okay. So you can see how the response of the LTI system, the magnitude response, is changing based on where the 0 is located. I hope you are comfortable with what we're seeing here. Okay. Now, what about the phase response of that? Supposing we are interested in the argument of the phase. So here we find that both the pole and the 0 will contribute. So if you look at the vector v1, let us say that angle has got angle omega, because that's what, that's how the point is moving around the unit circle. So argument of h e of j omega, h e of j omega will be equal to the angle of the phasor v3, because that's the numerator angle, minus the angle v1. Okay, so basically looking at a difference of two quantities. Okay, and maybe it's good for us to sketch these also. Okay, what is angle v1? Angle v1 starts at 0 and then goes all the way to 2 pi, straight line. So basically this is, if you say that this is 2 pi, goes from 0 to 2 pi. Basically as you go along omega, the angle of v1 goes from 0 to 2 pi. On the other hand, angle of v3 changes. How does it change? It starts out by being negative. Why negative? Because it is below the horizontal line. So basically this angle will be minus phi 3, or if you take it as phi 3 is the angle going in the counterclockwise direction, this angle will be minus phi 3. So it starts out by being negative. Okay, and as this point comes closer to the 0, notice that this angle becomes less and less negative. And eventually the angle touches 0, okay, and then becomes positive. So at the point at theta, this is the point theta. Okay, so it starts out by being negative, and at this point it takes on the value theta. And at this point both the omega and theta are aligned, so therefore their difference will go to 0. Okay, so eventually what you want to do is to take the difference between, so this is angle v3, the green one is angle of v3, v1, and the blue is angle of v3. Okay, so then what happens then at pi minus theta, pi plus theta, once again both of them are the same angle, and then eventually it goes down. Okay, it goes to some value, and No, actually it should come back to the place where it started. So let me make sure I get that correctly. Okay, so basically what you're seeing is there is a variation that happens. It starts at some negative value, goes all the way down, becomes positive, then eventually goes negative again. So now you can take the difference of these two quantities, and then you can get what is the overall argument of or the phase of the first order term. So the overall phase, if I were to sketch, again it's a rough sketch going from 0 to 2 pi. Initially it is negative, then at theta it becomes 0, and then at pi plus theta again it becomes 0, pi plus theta it becomes 0, and then goes on. So this is the argument of h e of j omega. Okay, I hope you are comfortable how to do that. Just like we did for the magnitude, look at the magnitude of the numerator divided by the magnitude of the denominator. Denominator is always equal to 1, but phase, both denominator and numerator contribute, so you see some variation in the phase. But for now, let us zero in and focus on the magnitude response that we are looking at. So this is what we are able to study. Now let us take a special case where we look at the location of the pole or the 0 on the unit circle. Okay, so this is on the unit circle. So if I were to sketch it, the 0 is sitting on the unit circle at z equal to -1, the pole is sitting here. Okay, now this is a good example for us to try out. So what is the radius of the 0? Radius of the 0 is equal to 1, right? So if you say that, what did we call the, we called it C0. C0 is equal to, in this particular case, equal to -1, right? C0 equal to, -1. This is the location of the 0, it's at z equal to -1. Now, what would you expect when you look at this particular magnitude response? Magnitude response starts out at a maximum value because the omega equal to 0 is maximum distance away from the 0. Then as you come closer and closer to the unit circle, it will become smaller and smaller. Eventually it will become 0. So if you were to plot it on a linear scale, this is what it will happen. Maximum value, it will come down, touch 0 at pi, and then again rise up, go back to maximum value. Okay, this is what we are seeing in terms of the response that you have when you plot it on a dB scale. 0 goes to -infinity. So basically it becomes a very large negative number. So you can see how the magnitude response goes like a waterfall. On the other hand, if I change this C0 to be equal to -0.9, that means it's not on the unit circle but very close to the unit circle. Then what you find is that the magnitude response does not go to -infinity but goes to some small value. So the second plot for 0.9 will come something like this. Okay, on a dB scale it looks a little different. So this is for 0.9. Then if you say that I'm going to only 0.5, then what happens, you will see that the behavior of the 0 location looks a little bit different. More important, want you to look at what will happen to the phase. Okay, the phase goes through a very, very interesting analysis. You need to be very careful in terms of understanding how the phase will behave. So let us look at whether we can get this phase response in a careful, accurate manner. Let me just give you an indication of how to do that, and then in the next session we will pick it up and look at how to analyze this. Okay, when you start at omega equal to 0, this is the same direction for both. Remember, the 0 is located here, the pole is located here. Both of them are pointing in the same direction, the phasors. Difference of them will be 0. So your starting point is at 0. Now as you go from 0 towards pi by 2, okay, notice that the pole angle is increasing faster than the 0 angle, because the 0 is further away from the. So as you go, let us take a point on this at this location. This is the angle omega. This is omega. This is theta. Okay, notice omega is larger than theta, so basically it's theta minus omega, so therefore it starts to become more and more negative. Okay, now as you approach the 0, it becomes very interesting how you have to analyze this. Okay, I want you to take a closer look. So now I'm starting to approach the point that of interest is, let us say, is here. Okay, what is the contribution of the pole? Almost 180 degrees, right? It's almost 180 degrees. What is the contribution of the 0? It is 90 degrees. This is 90, almost 90 degrees. So what we have is the angle, which is the 90 degrees is the contribution of the 0 minus the contribution of the pole, which is 180 degrees. So 90 minus 180, you will start to approach minus pi. Okay, so basically you are going to be touching minus pi. Okay, so this is the point at which you are going to, you're touching pi by 2. So that is the angle that, but the minute you cross the 0, go from this side to this side, something very interesting happens. What is the angle that that the pole is contributing is still close to 180 degrees. But what is the angle that the 0 is contributing? It is now minus 90. So once you cross this region, it will be minus 90, or in other words, minus 90 or 270. 270 minus 180, that will be plus 90. So you see that the minute you cross, you will jump from minus pi by 2 to plus pi by 2. Okay, this is plus pi by 2. So you see that there is a sort of a discontinuity in terms of the phase. And remember, we said wherever there is a rapid change of magnitude will also correspond to rapid change of phase. You can see an ideal example of this rapid change of magnitude as you approach the 0, rapid change of magnitude, correspondingly you see rapid change of phase. Now if you were to calculate the group delay, you will find that the group delay is more or less constant rest of the frequencies, but as you come close to the 0, you see that there is a big decrease in the group delay. Why? It's a negative of the phase change. The phase change is positive. It's going from minus pi by 2 to pi by 2. So therefore the group delay will be negative. So it will basically, if it is 0 for most of the case, it is now falling to some negative value. So what are the key observations that we are seeing here? Okay, first one is how to sketch the magnitude response. Magnitude response. Second is, we said how we can sketch the phase response, looking at various points as you go from the, so get the phase response. And looking at the magnitude response and the phase response and seeing where there is a large rate of change of phase, you say that that is where the group delay is going to be large. And therefore, this is the way by which we are also able to make some predictions about the group delay. Where the group delay, we can always compute it, but this is where we are going to look at. So now that we have got a good understanding of how to analyze the magnitude and phase of a first order 0, now I want to extend it to a first order pole and then eventually to a second order system. So that is what we would like to do. Again, many new concepts in today's class. I want you to take a careful analysis, or repeat all the calculations that we have done. If there are any doubts or questions, please contact Mr. Tony and clarify them during the discussion session. But this is an important chapter where we are going to now start to look at how to design LTI systems, and all of the things that we have studied in today's lecture and in the next session are going to be very helpful for us to be able to implement and design these LTI systems. So we will stop here and pick it up from this point. And so please look at the aspects that what we have done. We have looked at what is the frequency response of an rational transfer function, and we have also looked at what is some of the properties of an all-pass system. And in the next session, we will be building on this further and working our way towards a very important class of LTI systems, which is called the linear phase systems. And that is what will be the focus of our study. And with that, we will complete chapter 5 and then move on to the next chapter, which will be based on the discrete Fourier transform. Okay, we will stop here and pick it up in the next session. Thank you.